Welcome to Cosmic Sedation, your peaceful retreat from the day's noise. Tonight, we explore why space is silent, the soundless echo of a galactic collision, diving into the mysteries that whisper through the vastness of space. If you enjoy these journeys with us, please subscribe and like. Your support means the universe to us. As the stars align, let this calm wash over you. We begin our journey now. The soundless void of space is not just a lack of atmosphere. It is a consequence of physics itself. At -270 degrees Celsius, far below the freezing point of any known gas, even the rarefied hydrogen and helium that fill interstellar space are too sparse to carry sound waves. This silence persists despite the continuous gravitational dance between celestial bodies, where planets orbit stars and galaxies collide. Imagine two galaxies, each containing billions of stars, on a collision course. The Milky Way and Andromeda are moving towards one another at 402,000 kilometers per hour. Yet, as they approach, no sound precedes their eventual embrace. This is because the vacuum between them offers no medium for sound to travel through. Even if there were an observer in a spacecraft equipped with speakers, the silence would remain absolute. The gravitational dance of celestial bodies shapes space itself. Stars orbit within galaxies, tracing paths influenced by the collective gravity of billions of others. Each star follows its own unique trajectory, governed by forces that stretch back 13.8 billion years to the Big Bang. The Sun, for instance, takes about 225 million Earth years to complete one orbit around the galactic center. This dance is so precise and predictable that it allows astronomers to chart celestial paths with incredible accuracy. Consider a human observer floating in this silent expanse. If they were to shout, their voice would not carry beyond their own helmet. The silence is profound because space itself is devoid of any medium capable of transmitting sound waves. Yet, the gravitational forces at play are immense. A person near a black hole's event horizon experiences tidal forces that stretch and compress them, an effect known as spaghettification. This extreme environment underscores the paradox. While silent, space is far from empty. In this silence, galaxies collide without any audible fanfare. When galaxies merge, their stars rarely come into direct contact due to the vast distances between them. Instead, they weave through each other like ribbons in a cosmic ballet, influenced by gravity alone. These collisions can trigger bursts of star formation and even supermassive black hole mergers. Despite this frenetic activity, space remains silent because sound requires a medium, and there is none. The silence of space extends beyond the present moment into deep time. In 4 billion years, the Milky Way will collide with Andromeda, reshaping both galaxies in an event that will last millions of years. This cosmic dance continues long after human lifetimes have passed. Each star's journey through the galaxy is a testament to the enduring gravitational forces that shape the universe. Yet, for all its complexity and grandeur, space remains silent, a void where sound cannot exist. In this vast silence, consider the intricate ballet of planets within our own solar system. Jupiter and Saturn, the gas giants, exert gravitational forces that subtly influence each other's orbits, creating resonances that are both precise and ancient. These resonances have persisted for billions of years, a testament to the stability of their mutual dance. The gravity between them is so powerful that it shapes not just their own paths, but also those of smaller bodies like asteroids and comets. This gravitational interplay can fling some of these objects into distant regions of space or even towards Earth's orbit. Yet, despite this constant choreography, there is no sound to accompany the movement. The orbital periods of Jupiter and Saturn are 12, 5 years respectively, a ratio that has remained consistent for eons. This resonance is so stable that it could outlast the Sun itself. For an observer floating near these giants, the silence would be profound. They might witness the subtle shifts in gravitational fields as planets pass by, but no sound would accompany this cosmic waltz. The human body, sensitive to vibrations and pressure waves, would remain oblivious to the symphony of forces that govern their motion through space. This silent dance is not just a matter of absence. It is a fundamental property of the universe itself, where gravity reigns supreme without the need for sound to convey its influence. At precisely -270 degrees Celsius, the temperature in deep space is so cold that sound waves cannot propagate through it. This extreme chill causes atoms and molecules to vibrate at such low frequencies they cease interacting with each other as needed for sound transmission. In this environment, if you were to shout, your vocal cords would create vibrations, but find no medium dense enough to carry them. The vacuum of space is not merely silent, it actively suppresses the possibility of sound. Yet on Earth, we take for granted that air molecules are constantly in motion, bustling about like frenzied particles. This constant agitation is what allows us to hear sounds, from a whisper to an explosion. Consider this. While sound cannot travel through space's vacuum, light can traverse these vast distances unhindered. Light waves do not require a medium. They ripple through the fabric of spacetime itself. This peculiar property of electromagnetic radiation allows distant stars and galaxies to communicate across billions of years. Yet, for all its silence, space is far from empty. It teems with particles, protons, electrons, even the occasional hydrogen atom, that drift in these near-absolute zero temperatures. The cosmic microwave background radiation, a remnant from the Big Bang, permeates this void, though it too cannot convey sound. Imagine being an astronaut floating outside your spacecraft, far beyond Earth's atmosphere. You'd be surrounded by this silence, a profound absence of auditory cues that we rely on to orient ourselves in our daily lives. This sensory deprivation could induce disorientation or even anxiety for some individuals. In contrast, the human body is finely tuned to respond to sound waves. Our ears convert these mechanical vibrations into neural signals that our brain interprets as sound. Without this familiar input, your sense of space and time might feel distorted, a sensation akin to being in an echo chamber where no sound bounces back. Astronomers often use radio telescopes to listen to the universe, but they are not detecting sound waves in the traditional sense. Instead, these instruments capture electromagnetic radiation at radio frequencies, which can be translated into audio signals for analysis. This process transforms invisible cosmic phenomena, pulsars, black holes, and distant galaxies, into audible patterns that researchers study. Yet, this indirect listening to space does not equate to sound traveling through a medium. It is more akin to reading the universe's diary written in radio waves. It raises an intriguing question. If we could somehow introduce air into deep space, would sound then travel? The answer lies in the physics of pressure and density, which are fundamentally different between Earth's atmosphere and the vacuum of space. The absence of sound in space has profound implications for our understanding of cosmic events. For instance, when two galaxies collide, their stars do not crash into each other because they are spaced too far apart on galactic scales. However, this collision generates shock waves that ripple through the interstellar medium within these galaxies. These shock waves can compress gas clouds, triggering star formation at an accelerated rate. While these events are silent in terms of sound, they are anything but quiet when observed through other means: radio emissions, X-rays, and visible light from newly formed stars. This paradox underscores how our perception of silence is deeply tied to the physical properties of the universe. In 1 billion years, space will continue its silent journey, with galaxies drifting farther apart as the expansion of the universe accelerates. Stars will burn out or collapse into black holes, and new ones will form from clouds of gas and dust. Yet, throughout this vast timescale, sound waves will remain trapped within their respective mediums, planetary atmospheres like Earth's, or perhaps on exoplanets yet to be discovered. The silence of space is not just a consequence of its emptiness, but also a testament to the fundamental nature of physics that governs our universe. It challenges us to reconsider what we mean by sound and how it relates to our experience of reality both here on Earth and across the cosmos. Invisible to the naked eye, interstellar gas clouds are vast reservoirs of hydrogen and helium drifting in the void between stars. These clouds are not static. They are dynamic environments where particles collide and coalesce under the influence of gravity. 1 billion years ago, these clouds were denser and more numerous, their collisions driving the formation of new stars. Today, as we observe them from Earth, they have thinned out and spread across the galaxy, a testament to ongoing stellar birth and death. Every cubic meter of these ancient clouds contained trillions upon trillions of atoms, each one an invisible dancer in a cosmic waltz that shaped our galactic neighborhood. Yet, compared to the vastness of space, even this density is sparse, so thin that light can travel unimpeded for millions of years before encountering any significant obstacle. This transparency allows astronomers today to peer deep into these clouds and study their structures. The same process that birthed stars 1 billion years ago continues now, though at a slower rate as the gas becomes more diffuse. These cloud systems are not passive observers in space's grand ballet. They actively participate by contributing to cosmic microwave background radiation. As particles within these clouds interact with photons left over from the Big Bang, they subtly alter their energy levels, a phenomenon known as the Sunyaev-Zeldovich effect. This interaction, though minuscule on an individual particle level, accumulates across trillions of miles of space, influencing how we perceive the early universe today. This process underscores our connection to distant epochs through these subtle yet profound interactions. The transformation from dense gas clouds into sparse interstellar medium has implications for the formation of planetary systems as well. Billions of years ago, the concentration of materials in these clouds facilitated rapid star and planet formation. Today, with less material available, stars form more slowly, allowing planets to develop under different conditions. This gradual thinning out means that future generations of stars may have fewer raw materials at their disposal for planetary systems, potentially leading to a cosmos where life-friendly worlds become increasingly rare. Studying these gas clouds also reveals the presence of complex molecules, including organic compounds essential for life as we know it. These molecules form through chemical reactions within the clouds, catalyzed by cosmic rays and ultraviolet light from nearby stars. A billion years ago, such reactions were more common due to the higher density of materials available. Today, while less abundant, these processes still occur, suggesting that the ingredients for life are continuously being synthesized across vast reaches of space. This ongoing synthesis hints at a universe perpetually preparing the ground for new beginnings. Observations from modern telescopes show that these clouds are not uniform, but instead structured into filaments and clumps. These structures form due to gravitational instabilities within the cloud, leading to regions where matter accumulates more densely than elsewhere. As time progresses, these denser regions will eventually collapse under their own gravity, igniting new stars. This cycle of formation and dispersal has been ongoing for billions of years, shaping the galactic landscape we see today. In the heart of our galaxy, two black holes are spiraling toward each other, their immense gravity distorting space-time itself. They are invisible to optical telescopes, but detectable through the ripples they send out, gravitational waves that stretch and squeeze the fabric of reality as they pass by Earth. Yet, in this cosmic dance of destruction, there is no sound. The collision of these massive objects will release more energy than all the stars in the universe combined, yet it would remain silent to human ears. This paradox emerges from a fundamental property of space itself. Sound requires a medium such as air or water to propagate through. In the vacuum between celestial bodies, there is nothing for waves to travel on. Even if we could somehow hear gravitational waves, they are not pressure variations in any conventional sense. The energy released during this collision would be equivalent to millions of supernovae exploding simultaneously, yet it remains a silent spectacle, invisible and inaudible. Imagine the quietest moment you've ever experienced. Now imagine that silence amplified across an entire galaxy. As these black holes merge, they create ripples in space-time that stretch and compress distances on Earth by less than 1 part in 10 trillion. For context, if we could measure this distortion with perfect accuracy, it would be like noticing the difference of a few atoms in the length of the Great Wall of China. This minute change is detectable only through extraordinarily sensitive instruments designed to pick up these subtle movements. The universe's loudest events are thus experienced on Earth as an imperceptible wobble. Consider now the scale at which we perceive sound. Our ears can only register frequencies between approximately 20 and 20,000 hertz. In contrast, the frequency of a typical gravitational wave from such an event would be around 1 cycle per second, far too slow for human hearing. Yet this slowness is what allows us to detect it at all. If these waves were faster, they might pass through detectors unnoticed. The universe's silence becomes a tool for discovery, revealing itself through methods far beyond traditional senses. During the collision of those black holes, matter heats up to temperatures hotter than any found on Earth or even in stars, reaching billions of degrees Celsius. Despite this intense heat, there is no sound because sound needs particles to vibrate and carry its energy. These extreme conditions produce light across a spectrum from gamma rays to radio waves, but not the kind of compression waves that form sound. Instead, imagine standing close to a firework explosion. You feel the pressure wave before you hear it. In space, there is no pressure wave at all. The aftermath of such an event leaves behind a single, larger black hole, a remnant of cosmic violence. This new entity continues to distort space-time around it, but still without producing any sound. It's as if nature has conserved energy in this collision, not only through gravitational waves, but also by withholding the usual accompaniment of noise. In this way, silence becomes a kind of conservation law, preserving the universe's resources even amidst its most dramatic transformations. In the vacuum of space, sound cannot travel because there is no medium for pressure waves to propagate through. To understand this absence fully, imagine standing on the surface of the Moon during an ongoing collision between 2 distant galaxies. While the cosmic event would emit radio waves and light visible from Earth, your ears, attuned to frequencies in air or water, would detect nothing. This sensory deprivation is not merely a lack of noise, it's a profound shift in how we perceive our surroundings. The human ear evolved to capture vibrations through air molecules, but space lacks this molecular soup. Instead, the silence you hear, or rather, don't hear, would be an eerie echo of your own expectations colliding with reality. In the vacuum between stars, sound waves from a distant supernova would never reach you. Now consider for a moment the human body's response to such profound quiet. If you were in space without a spacesuit, the silence wouldn't just be about the absence of sound. It would also encompass the immediate threat of decompression and exposure to extreme temperatures. The sensation of cold on your skin, approaching minus 270 degrees Celsius, would feel like an unyielding chill that no insulation could fully shield against. Yet, even as you shiver in this life-threatening environment, your mind might still yearn for the familiar hum of a distant engine or the faint rustle of leaves. In contrast to space's silence, Earth is a symphony of vibrations. Airborne sounds from birdsong and machinery, seismic waves traveling through rock. Even when we sleep, our bodies are bathed in low-frequency vibrations that can influence our dreams. In space, these vibrations vanish entirely, leaving only the stillness of an infinite void. The absence of sound here is total, not just a quiet, but a profound emptiness that echoes across eons. Imagine this silence as a kind of cosmic stasis. Stars are born and die in this vacuum with no auditory witness. Their life stories unfold without the accompaniment of sound. Yet, these silent processes shape everything around us. The elements in our bodies were once forged in ancient stellar explosions. This silence is not just an absence, but a reminder of the vast timescales on which cosmic events occur, far beyond human perception. As you drift further from Earth's atmosphere, this silence becomes more pronounced. The vacuum of space is so devoid of sound that even the faintest whisper would remain unheard. In this environment, your sense of hearing might adapt to other stimuli, perhaps vibrations through your spacesuit or radio signals from home. In the vastness of space, the absence of sound is not merely a quiet. It is an unyielding void that presses against every sense but cannot be heard. Were you to float freely without a spacesuit, the silence would be accompanied by the disorienting awareness of your own heartbeat echoing in your chest, an internal rhythm that becomes more pronounced in the absence of external sounds. This isolation from auditory cues can induce a peculiar form of sensory overload, as your brain struggles to process the lack of familiar stimuli. On Earth, sound provides constant feedback about our surroundings, whether it's the rustle of leaves or the hum of distant traffic. In space, this continuous stream of information is severed, leaving you suspended in an environment where even light moves at a speed that seems instantaneous by human standards. Yet, paradoxically, while the vacuum of space offers no sound, it does carry other forms of communication. Radio waves and electromagnetic signals can traverse the void, connecting distant points in our universe through invisible threads. These signals travel across billions of kilometers, offering a different kind of connection to places that are otherwise unreachable by any physical means. The silence you experience is thus not just an absence, but also a bridge between worlds, carrying messages from Earth to distant spacecraft and back again. In interstellar space, atoms and molecules collide with remarkable frequency despite the vast distances between them. These collisions occur at speeds of thousands of kilometers per second, yet they rarely generate sound as we know it. Instead, the energy from these atomic interactions is released in other forms, most notably across the electromagnetic spectrum. This radiation spans a wide range, from high-energy gamma rays to low-frequency radio waves. Each collision is a microscopic event, but when multiplied over billions of years and countless particles, the cumulative effect shapes the universe's very structure. Consider this. While sound cannot travel through the near vacuum of space due to the lack of molecules to carry pressure waves, electromagnetic radiation faces no such barrier. It can traverse the emptiest reaches of the cosmos at light speed, carrying information about distant stars and galaxies across billions of years. This means that the particles colliding in interstellar space are not just silent, they are also storytellers, each collision a tiny whisper of energy that travels vast distances to inform us of their existence. Yet for humans confined to Earth's atmosphere, these collisions remain invisible and unheard. Atomic collisions in space do more than emit radiation. They create heat. This phenomenon is crucial for understanding the life cycles of stars and planets. When atoms collide at such high velocities, they can fuse or split apart, releasing energy that heats their surroundings. In stellar nurseries, where clouds of gas collapse under gravity to form new stars, these collisions are essential for initiating fusion reactions. The resulting heat and light from these young suns eventually illuminate the darkness around them, marking a stark contrast between silent atomic interactions and the radiant glow of star formation. Paradoxically, while space is devoid of sound, it is not entirely mute in its effects on human perception. Satellites equipped with instruments sensitive to various forms of radiation can detect signals from these collisions across great distances. These detectors translate invisible electromagnetic waves into audible frequencies, creating a kind of sonification that allows us to hear the universe's silent whispers. This process transforms raw data into soundscapes, offering listeners an auditory representation of cosmic events, though not true sound as we experience it on Earth. As these particles collide and emit radiation, they also contribute to the background glow known as the cosmic microwave background, CMB. This faint afterglow is a remnant from when our universe was only about 380,000 years old. At that time, the universe cooled enough for protons and electrons to combine into neutral atoms, releasing radiation that has been traveling through space ever since. The CMB provides a snapshot of the early universe in its infancy, revealing details about its composition and evolution long before stars or galaxies formed. In regions where new stars are born, such as the Orion Nebula, atomic collisions play an intricate role in shaping the eventual fate of these stellar nurseries. As gas clouds contract under gravity, they become denser and hotter, leading to increasingly frequent collisions among atoms. These interactions not only release radiation, but also help seed magnetic fields within the nebula. Over time, these fields influence how matter coalesces into stars and planets, subtly guiding the architecture of entire solar systems from the smallest atomic scales upwards. Thus, while silent in sound, atomic collisions in space are the quiet architects of cosmic creation. Amidst the silent embrace of space, astronauts aboard separate spacecraft face an unexpected challenge: communication without sound. Each module floats within its own bubble of near-perfect vacuum, where pressure waves cannot propagate. This absence of air makes it impossible for voices to travel in the usual way, yet human ingenuity has found a workaround through radio waves. Radio signals, unlike sound waves, do not require a medium to travel. They are electromagnetic waves that can traverse the emptiness of space with ease. The same principle that allows us to listen to distant galaxies also enables astronauts to talk to each other across vast distances within their spacecraft. This technology is not just practical. It's essential for survival in environments where sound would be as useless as a telephone underwater on Earth. Consider this. While radio waves can travel through the vacuum of space, they still face challenges beyond mere transmission. Each signal must contend with background radiation from cosmic events like supernovae and black holes, which can sometimes obscure or alter their path. Yet, despite these interstellar whispers, communication systems aboard spacecraft are finely tuned to filter out noise and ensure clear messages reach their intended recipients. For astronauts in different parts of the same spacecraft, this lack of direct sound transmission means they must rely on radio for even simple exchanges within close proximity. This can create a subtle disconnect, as if speaking through a barrier that isn't just physical, but also temporal and spatial. The very act of communicating over such short distances mimics the challenges faced when contacting distant planets or moons. Intriguingly, this reliance on technology for communication mirrors how we might one day interact with extraterrestrial life forms, should they exist. Should a signal be intercepted from an alien civilization, it would likely be in the form of radio waves, not sound. This raises questions about the universality of language and whether there is a fundamental limit to what can be conveyed through purely informational signals. While astronauts within different modules must use radios for communication, the silence between them also serves as a reminder of the vast distances they cover even within their shared spacecraft. The space between them is not just physical but metaphorical, a quiet zone that separates individuals despite being part of the same mission. This silence, however, does not signify isolation. Rather, it underscores the intricate network of communication that binds them together in the most profound sense. In this environment, where sound is rendered obsolete, time itself can feel distorted for astronauts. The absence of ambient noise means they are cut off from many of Earth's familiar auditory cues that help us gauge passage. No ticking clocks, no distant traffic hums, and certainly no whispers of wind or rustling leaves. Instead, the only sounds inside a spacecraft come from mechanical systems. Fans whirring, life support equipment operating, and the occasional soft beeps from computers. These artificial noises create a unique auditory landscape that serves as both comfort and reminder of their isolation. Yet, outside this cocoon, time unfolds differently. The vastness of space means distances between objects can stretch for light years, making real-time communication with Earth or other distant spacecraft an exercise in patience. Signals sent from one astronaut to another may take fractions of a second to traverse the short gap within their craft, but could take minutes or even hours if they were communicating across solar system scales. This delay underscores the profound isolation that astronauts experience. Though connected by technology, the sheer scale of space ensures they are always just slightly out of sync with both Earth and each other. Despite this temporal disconnect, however, there is a strange comfort in knowing that every beep, every radio transmission, travels through the same void that connects all human-made objects in space. This shared silence serves as an invisible thread binding them together across unimaginable distances, a silent chorus where each signal carries not just words, but also echoes of their collective endeavor to explore the cosmos. Consider the distance between stars as an unfathomable expanse, far beyond our everyday comprehension. The average gap between two stars in our galaxy is approximately 4 light years. To grasp this scale, imagine holding a single strand of human hair at arm's length. Now, envision that each individual hair represents the width of the space separating you from your nearest stellar neighbor, Alpha Centauri. This minute comparison underscores both the vastness of interstellar distances and the intimacy of our own microscopic world. The paradox arises when we consider how densely packed stars are within their clusters compared to this cosmic isolation. In a globular cluster like Omega Centauri, approximately 1 million stars crowd into a space roughly 150 light-years across. This concentration stands in stark contrast to the solitary existence of most stars in our galaxy. The sheer density here challenges our intuitive sense of emptiness in space, revealing that while star systems are often lonely outposts, clusters can be bustling hubs where stellar encounters occur with relative frequency. Let us now focus on a particular event occurring in this cosmic arena, a galactic collision. When two galaxies like the Milky Way and Andromeda collide billions of years hence, they will do so over a period of about 4 billion years. This process is akin to a slow-motion dance, where each galaxy carries its own stars, gas clouds, and dark matter on trajectories that span unimaginable distances. Despite this vast scale, the actual interaction between individual star systems within these galaxies remains rare due to the immense separations we've discussed. The collision will be more of a gentle embrace than a direct encounter. Imagine now an astronaut floating in space near one of those distant stars. At 300,000 kilometers per second, light travels from this remote stellar body to reach our observer. Yet, despite traveling at the fastest possible speed, it takes years for even nearby stars' light to arrive. This delay highlights how our perception of distance in space is fundamentally different from that on Earth, where sound and light travel instantaneously over short scales, but are stretched into a temporal experience when considering cosmic distances. Returning to the initial comparison between stellar separations and human hair, it's worth noting the implications for future interstellar travel. If we were to build spacecraft capable of traversing these vast spaces at speeds close to that of light, the journey between stars would still take decades or centuries. This reality underscores the monumental challenge faced by any civilization attempting to explore beyond its own star system. The distances are not just vast in terms of kilometers, but also in the time and resources required to cross them. In considering these immense scales, it's striking to note how our understanding of space is constantly evolving with new discoveries. For instance, recent studies suggest that dark matter may play a crucial role in shaping galactic collisions, providing gravitational scaffolding that influences the interaction between galaxies. This discovery adds another layer of complexity to our conception of space, revealing that even within these vast voids, there are intricate forces at work guiding the dance of celestial bodies. Each star, despite its isolation, remains part of a larger cosmic tapestry, bound by invisible threads of gravity and dark matter. At the dawn of the universe, less than 400,000 years after the Big Bang, the cosmos was still too hot and dense for light to travel freely. The entire universe was a roiling sea of particles, photons struggling against the gravitational pull of matter. Today, this ancient radiation is detectable as cosmic microwave background, CMB, radiation. It fills every corner of the observable universe, an omnipresent afterglow from the birth of time itself. Yet, remarkably, it remains silent, a testament to how profoundly sound and light behave differently in the cosmos. The CMB has cooled to a mere 2.7 Kelvin above absolute zero since its initial formation. At this temperature, Any residual pressure waves that might have carried sound would long ago have dissipated into the fabric of space-time. This radiation is not just an echo of our universe's infancy. It is also a snapshot of what will eventually become the final state of our cosmos. As stars burn out and galaxies drift apart, the CMB will be all that remains, an invisible whisper from the beginning of everything. It is fascinating to consider how this silent remnant, born in a time when sound could not exist as we know it, now holds the key to understanding the origins of space and time. The distribution of this radiation across the sky reveals slight temperature variations, no more than 100 millionths of a degree. These minute fluctuations are crucial because they represent the seeds from which all cosmic structures, galaxies, stars, planets, were born. Each variation corresponds to areas where matter was slightly denser or less dense during the universe's earliest moments. If sound had existed then, it would have propagated through these variations like ripples on a pond, creating complex patterns of pressure waves that we cannot hear today. Instead, what remains is a faint glow detected by instruments like the Planck satellite, mapping the infant universe with exquisite precision. These temperature differences in the CMB are not random. They follow a specific pattern known as acoustic peaks. These peaks indicate how sound waves would have propagated if conditions had allowed for them. The largest peak corresponds to the distance that sound could travel before the universe expanded enough to freeze out these ripples. This distance is approximately 450,000 light-years across at recombination, the moment when the universe cooled down and became transparent to light. In comparison, our Milky Way galaxy spans about 100,000 light-years, suggesting that the scale of these acoustic peaks dwarfs even the largest structures we can observe today. The CMB also provides a unique window into the physics governing the early universe. By analyzing its polarization patterns, scientists have discovered evidence for gravitational waves, ripples in space-time caused by violent events like black hole mergers or the Big Bang itself. These waves, which are too faint to be directly detected on Earth, left an imprint on the CMB as a subtle twisting of light. The fact that we can infer such phenomena from this ancient radiation underscores how profoundly interconnected different aspects of physics remain across vast stretches of time and space. It is humbling to think about how much information about the universe's past is encoded in these faint microwaves. While sound cannot travel through the near vacuum of deep space, the CMB serves as a kind of cosmic soundtrack, carrying within it the history of our universe. Each photon that reaches us from this radiation has been traveling for billions of years, bearing witness to an era when the cosmos was much different than today. As you drift off into sleep tonight, consider how this silent echo from the dawn of time continues to shape our understanding of existence itself. The CMB is not just a relic. It is a living record that connects us to the very beginning of everything. In intergalactic space, where no air molecules exist to carry sound, our ears would remain silent. However, an entirely different kind of communication thrives here, one that doesn't rely on vibrations in a medium, but rather on waves that can travel through the vacuum itself. Radio telescopes detect these electromagnetic signals, which have traveled vast distances across the universe. These instruments are sensitive enough to pick up the faint whispers of distant galaxies, supernovae explosions, and even the leftover radiation from the Big Bang. The human ear cannot hear these frequencies, but they tell us stories about events that occurred billions of years ago in regions light years away. Returning to our immediate surroundings, this silent space is not completely devoid of information. Instead, it becomes a canvas for invisible waves. Consider the Event Horizon Telescope, an international collaboration using radio telescopes scattered across the globe. This network works together as one giant telescope with a diameter equal to Earth's circumference, capturing images of black holes at the centers of galaxies. The signal strength diminishes significantly over such vast distances, yet the precision required for detecting these faint signals is remarkable. Each dish collects microwaves emitted from distant quasars and radio sources, which are then combined to form detailed maps of cosmic structures invisible to optical telescopes. This process underscores how our perception of silence in space is merely a limitation of human sensory biology rather than an absence of information. Back in the quietude between stars, these instruments continue their vigil, quietly listening for the universe's hidden secrets. Astronomers use radio waves not only for passive observation, but also to actively probe cosmic phenomena. By sending out precise signals and measuring their reflections, scientists can map celestial bodies with unprecedented accuracy. This technique, known as radar astronomy, has been used to study our nearest neighbor, Venus. Despite its thick atmosphere, the surface remains largely unknown due to cloud cover. Yet, by bouncing radio waves off the planet's surface, researchers have mapped out its topography and learned about its internal structure. The method works similarly for other planets and even asteroids, revealing details that would otherwise remain hidden from view. This form of active listening in space highlights how our understanding of distant objects is often contingent on technological ingenuity rather than direct sensory experience. In this context, the silence of space serves as a backdrop against which we can discern subtle echoes of cosmic events. The radio signals detected by these telescopes originate from various sources throughout the universe. Some come from pulsars, rapidly rotating neutron stars that emit beams of electromagnetic radiation like lighthouses. These beams sweep across space periodically, creating detectable pulses for observers on Earth. The timing precision of these pulses allows astronomers to study the extreme conditions near neutron stars and test theories about gravity and relativity. Each pulse carries information about the pulsar's rotation rate, magnetic field strength, and even its age. This stream of data arriving from across the galaxy provides insight into processes far removed from our everyday experience. Returning to the immediate silence around us, these signals remind us that while sound cannot travel through space, electromagnetic waves offer a different kind of auditory narrative. Interstellar space is not entirely empty. It contains sparse particles and magnetic fields that influence radio wave propagation. Electrons and protons left over from star formation or supernova explosions create an environment where charged particles interact with the Earth's magnetic field. These interactions produce auroras visible near the poles, but also generate detectable low-frequency radio emissions known as chorus waves. While these sounds are inaudible to humans, they provide valuable information about solar wind conditions and magnetospheric dynamics. The detection of such signals reveals that even in the vastness between stars, there is a structured environment governed by physical laws. This observation brings us back to our current location. Amidst this silent expanse, invisible waves carry stories of distant events, allowing us to eavesdrop on cosmic conversations. In addition to studying far-off objects, radio telescopes help monitor near-Earth space for potential threats like asteroids and comets. By tracking these celestial bodies with high precision, astronomers can predict close approaches and assess the risk posed by impact events. This capability underscores how technology has extended our senses beyond the limitations of human biology. The ability to detect faint signals across immense distances exemplifies the ingenuity required to explore the universe. As we continue to refine these instruments, they will provide ever more detailed insights into phenomena that would otherwise remain hidden from view. In this silent realm between stars, where no sound can travel, electromagnetic waves offer a unique form of communication, bridging the gap between Earth and the cosmos. Returning to our immediate surroundings, it is clear that while we might not hear anything in space, there is still much to listen for. On Earth, sound travels through a medium, air molecules that vibrate and transfer energy. This process allows us to hear everything from a whisper to a thunderclap. In space, however, there is no air. It's an environment bereft of any atmosphere. Consequently, when two spacecraft pass each other at a distance of just a few meters in the vacuum of space, they remain utterly silent, even though their relative velocities might exceed 20 kilometers per second. The silence here is not merely a lack of noise, but a profound absence of any medium through which sound could propagate. This stark difference between Earth and space highlights how integral air is to our auditory experience. Consider the human ear. It's exquisitely adapted for an atmosphere rich in molecules. Yet, in the vacuum of space, this adaptation becomes redundant. Sound waves require particles to vibrate against one another, but there are no such particles outside Earth's protective envelope. In fact, if you were floating in space without a spacesuit, your own vocal cords could vibrate all they wanted, yet nothing would carry that vibration into the surrounding void. This might seem like an obvious point, but it underscores how deeply we rely on our environment to experience sound as we know it. The contrast between Earth's noisy atmosphere and the silent vacuum of space is a striking reminder of our planet's unique qualities. The silence in space is not just a consequence of its emptiness. It also reflects the immense scale of cosmic distances. When you look at distant stars, you might imagine their light traveling through a medium that carries sound. However, the sheer vastness of interstellar space means that any particles present are so sparse as to be nearly irrelevant for transferring vibrations. On average, there is 1 particle per cubic centimeter in the void between galaxies, compared to millions or even billions of molecules in Earth's atmosphere at sea level. This scarcity makes sound propagation impossible over such great distances, a fact that underscores how deeply our everyday experiences are tied to the specific conditions on our planet. In space, communication relies heavily on radio waves instead of sound, as these can travel through the vacuum without needing a medium. Yet, this shift in communication methods doesn't negate the profound silence around it. Imagine two astronauts floating next to each other in orbit. They cannot hear each other speak unless using radios or tethered helmets that allow for vibrations to transfer through solid materials. This dependence on technology is a stark reminder of how differently we must approach life outside our atmosphere. The silence isn't merely an absence, but a necessity, shaped by the physical properties of space itself. The role of air in sound transmission becomes even more apparent when considering how sound behaves within Earth's atmosphere. At sea level, where air pressure is highest, sound travels at approximately 343 meters per second. As altitude increases, however, the density and pressure of the air decrease, slowing down the propagation of sound waves. This phenomenon can be observed in high-altitude environments like mountains or aircraft cabins flying above 10 kilometers. Here, the reduced air density not only makes it harder for sounds to travel, but also causes them to become fainter more quickly with distance. In space, this effect is taken to its extreme, where there is virtually no atmosphere at all. Interestingly, while sound cannot travel in the vacuum of space, certain objects can still create vibrations that could be detected under different circumstances. For instance, if two spacecraft were to collide, they would generate shock waves through their structures, but these internal vibrations wouldn't propagate into the surrounding vacuum. Instead, such collisions might be recorded using sensitive instruments on board or by remote sensors, allowing for a form of detection that bypasses the need for sound. This highlights how our understanding and interaction with space must evolve to accommodate its unique properties, including its profound silence, a silence that is both an absence and a necessity in this vast, empty domain. When two black holes collide in deep space, an event so cataclysmic that it would outshine entire galaxies for fleeting moments, the fabric of space-time ripples like water disturbed by a stone. These gravitational waves travel at the speed of light, distorting everything in their path. Yet, not a single sound is produced. This cosmic dance remains silent to all but the most sensitive detectors on Earth. The collision itself generates no pressure variations in the vacuum of space. Each black hole has an event horizon where light cannot escape, that warps space-time around it. Strangely enough, the nearest such event occurred over 1 billion years ago, and its effects are only reaching us now. We detect these signals not through sound, but via laser interferometers like LIGO, which measure minute distortions in space. The energy released during this collision is equivalent to the mass of several suns, converted entirely into gravitational radiation, a process that would outstrip even our most powerful nuclear weapons by unfathomable degrees. This cosmic energy surge, however, remains silent, a reminder of how space-time itself carries information rather than sound. The event horizon of a black hole acts as a boundary where time and space cease to have meaning as we understand them. As matter falls toward this point of no return, it stretches into a long stream known as an accretion disk, before disappearing entirely beyond the threshold. Within this region, not even light can escape, let alone sound waves that require particles for propagation. The black hole consumes everything around it with perfect efficiency, yet remains silent in its voraciousness. It is in these moments of cosmic violence where we see how silence can be a more powerful force than any imaginable noise. During such a collision, the two black holes spiral inward, their orbits tightening until they finally merge into one larger entity. This process takes place over thousands to millions of years for supermassive black holes and mere milliseconds for smaller ones. As they draw closer, the rate at which spacetime is distorted increases exponentially, causing ripples in the fabric of reality that propagate outward like shockwaves, but still remain soundless. The energy released during this merger can be so intense that it briefly outshines all other sources of light in the universe combined. While these collisions are silent to us, they do leave behind a trail, a gravitational footprint etched into spacetime itself. These waves travel across billions of light years and allow us to detect events long after they have occurred. The signal from one such event took 130 million years to reach Earth, giving scientists a glimpse into the distant past with each detection. Each ripple carries information about the masses, spins, and velocities of these cosmic giants, details that would be impossible to gather through traditional telescopes. Intriguingly, while black hole collisions are silent in space, they can indirectly create sound-like phenomena on Earth. When a gravitational wave passes through our planet, it causes tiny distortions in distances between objects, which can be detected using precision instruments. These effects might cause slight variations in the length of laser beams or microscopic shifts in mirror positions, phenomena that could theoretically produce audible signals if amplified. Yet, these sounds are far from what you would hear during a typical day on Earth. They exist at frequencies too low for human ears to perceive directly and require sophisticated technology to translate them into something akin to sound. Galactic collisions occur over timescales that defy human comprehension, spanning billions of years. These titanic encounters reshape entire galaxies, stretching and warping stars in the process. Yet, despite the violence of such an event, no sound is produced. The forces at play here are immense. Gravitational tides rip apart stellar nurseries, twisting galactic arms into intricate shapes. But for these forces to create audible sound waves, they would need a medium through which energy could propagate, something akin to air or water. In the vacuum of space, however, there is no such medium. Each star and galaxy moves independently within an expanse where matter is exceedingly sparse. To imagine this, consider that if our sun were placed in deep intergalactic space, it would be so isolated that its nearest stellar neighbor might be thousands of light years away. This vast emptiness means that even during a collision, the density of particles remains too low for sound waves to form or travel. It's a paradox. While these collisions exert forces powerful enough to change the course of galaxies, they do not generate any auditory echoes. As two galaxies approach each other, Their gravitational fields begin to stretch and pull at one another's stars and gas clouds. This process is akin to stretching taffy, a slow, steady deformation that can take millions of years to complete. The Milky Way, for example, is currently engaged in a collision with the smaller Andromeda galaxy. In just 5 billion years or so, these two will merge into one massive galaxy. During this time, stars will be hurled about like pebbles in a cosmic storm, but all within the silent vacuum of space. Despite the absence of sound, the violence of galactic collisions is not without consequence for those within them. Stars can be torn from their orbits, flung across vast distances, only to eventually settle into new ones or drift alone through interstellar space. These wandering stars are known as hypervelocity stars, moving at speeds far exceeding any star's usual velocity within a galaxy. They trace elegant arcs in the sky, evidence of cosmic upheaval. Yet, even these dramatic ejections occur without producing any sound that could be heard by an observer. When two galaxies collide, their central black holes play a crucial role in shaping the event's outcome. These supermassive black holes exert such powerful gravitational forces that they can merge with each other after the rest of the galaxies have combined. The process of this merger emits ripples through space-time itself, gravitational waves that propagate outward at the speed of light. However, these waves do not carry sound. Rather, they are distortions in the fabric of space-time itself, detectable only by highly sensitive instruments on Earth. It is a reminder that while we often associate collisions with noise and tumult, the universe has its own quiet ways of expressing violence. During a galactic collision, individual stars may pass within mere light years of each other, an extremely close encounter by cosmic standards. Yet, due to the vast distances between them, they rarely collide directly. Instead, these near misses can trigger waves of star formation as gas clouds are compressed and heated. This activity would be invisible from Earth, but for the intense radiation it emits, X-rays and ultraviolet light, that can be detected by telescopes. These collisions offer a glimpse into some of the most energetic processes in the universe, all unfolding silently against the backdrop of deep space. In the quiet solitude of space, radio telescopes stand as sentinels, listening for whispers from distant cosmic events. These instruments are designed to detect faint signals that traverse the universe over billions of years, signals that would be drowned out by sound in an atmosphere. The absence of noise is crucial for their sensitivity. In this silence, a single photon can carry information across galaxies, undisturbed by the cacophony of everyday life on Earth. Consider the vastness of space. Each signal captured by these telescopes has traveled through trillions upon trillions of kilometers to reach us. Yet, in the vacuum between stars, the noise that could interfere with such delicate measurements is non-existent. The human ear cannot fathom this silence. It is a realm where sound itself ceases to exist due to the lack of particles to transmit vibrations. This profound quiet is not just the absence of something, but an essential condition for observing phenomena far beyond our reach. Imagine, if you will, the complexity of filtering through cosmic noise on Earth. Radio telescopes must be shielded from terrestrial interference, everything from mobile phone signals to radar, and even the hum of fluorescent lights can overwhelm delicate instruments. In space, this challenge is absent. The silence provides a pristine environment for detecting faint radio emissions that tell us about distant stars, galaxies, and black holes. Each signal carries stories of immense cosmic events, offering insights into the universe's history. Astronomers use this quiet to map the invisible architecture of our cosmos. The dark matter bridges between galaxies, or the magnetic fields threading through interstellar clouds. These phenomena are not directly observable, but their effects can be inferred from subtle variations in radio waves. Without the vacuum's silence, these delicate signals would be lost amidst a sea of terrestrial noise. This environment allows scientists to study some of the oldest and farthest objects in the universe with unparalleled clarity. In this quiet void, space telescopes are akin to ancient explorers listening for distant drumbeats across an ocean. They gather data from sources so faint that even at their peak brightness, they would not be visible to the naked eye. For instance, a pulsar, a rapidly rotating neutron star emitting beams of radiation, can send out radio signals detectable only under these silent conditions. The precision required for such detection is akin to hearing a whisper in a storm-ravaged city from miles away. Each signal detected by these telescopes carries information about the universe's past and future, revealing details that would otherwise remain hidden beneath layers of noise. These cosmic echoes are not just random pulses, but structured patterns that carry messages across time and space. From the formation of stars to the expansion of galaxies, the silence of deep space is a crucial enabler for unraveling the mysteries of our universe's origins and evolution. The stillness allows us to listen to the faintest whispers from the cosmos, offering insights into phenomena we can barely imagine. The radio telescopes that operate in this silent expanse are not merely passive listeners. They actively sift through a cacophony of cosmic signals to isolate specific frequencies indicative of celestial events. Each antenna, precisely aligned and shielded from Earth's electromagnetic interference, captures minute fluctuations in the background radiation left over from the Big Bang, a remnant known as the cosmic microwave background, CMB. This faint glow, detected only by these sensitive instruments, provides a snapshot of the universe as it was approximately 380,000 years after the Big Bang. The silence of space allows for this remarkable clarity, enabling scientists to discern subtle variations in temperature that reveal the distribution of matter and energy at the dawn of cosmic structure formation. These minute temperature differences are akin to the ripples on a pond's surface caused by a pebble dropping into it. Each ripple represents a slight deviation from absolute uniformity. In this cosmic context, these deviations hint at the seeds of galaxies and galaxy clusters that would eventually emerge. Without the vacuum's silence, such delicate variations would be overwhelmed by terrestrial noise. The precision required to detect these minute fluctuations is astonishing. Changes as small as 1 part in 100,000 must be measured across vast distances. This level of accuracy is akin to detecting a change in temperature equivalent to a single degree Celsius over the entire surface of Earth. In this silent domain, Radio telescopes act as cosmic stethoscopes, listening for faint murmurs that tell tales of the universe's infancy. Each signal carries echoes from epochs when light itself was just beginning to travel unimpeded through space. These detections offer clues about how matter clumped together under gravity's pull, ultimately leading to the formation of stars and galaxies we observe today. This silent environment is crucial for understanding the fundamental processes that shaped our universe, providing a window into the unseen forces at work in the cosmos. Now consider this. At the exact moment two galaxies began their collision, light left that scene and is only now reaching Earth. This event occurred billions of years ago, yet it has just entered our telescopic view. The Andromeda Galaxy, a swirling mass of stars 2.5 million light-years away, is on a direct course toward the Milky Way. Every photon from this cosmic merger travels through time, arriving at its destination with an unerring precision. This moment of galactic contact represents a profound convergence not just in space, but also in time. The photons we observe today are messengers from epochs long past, bearing witness to processes that have shaped galaxies since the universe's infancy. These light-years-long journeys allow us to see deep into cosmic history. For instance, when this collision began, life on Earth was still a simple affair of single-celled organisms. Yet here we are, capable of observing these distant events with remarkable clarity. As we focus on the precise instant of collision, imagine the sheer number of stars involved. Each galaxy contains hundreds of billions of them. The density at the point of contact must have been staggering, comparable to a city where every building is a star. This concentration of matter would have produced an extraordinary gravitational dance, with each celestial body exerting its pull on countless others in a symphony of motion. The light we see from this cosmic embrace has taken 2.5 million years to reach us because space itself has expanded during that time. Each photon's journey is not just through empty void, but also through the vastness of an ever-expanding universe. This expansion stretches light waves, making them appear redder, a phenomenon known as redshift. The precise measurement of this color shift allows astronomers to gauge distances with remarkable accuracy, revealing the timeline of cosmic events. At the moment these galaxies began their collision, stars within both systems were forming and dying in a continuous cycle. Newborn stars burn brightly, while older ones collapse into black holes or supernovae. This ongoing stellar life cycle is an essential part of galactic evolution. Each star's existence influences its neighbors through gravity, radiation, and even the expulsion of enriched material that will eventually form new planets. This collision is not just a spectacle, but also a vital process in cosmic recycling. Stars within merging galaxies enrich their surroundings with heavy elements formed during their lives. These materials are essential for the formation of planets like Earth. When we look at this ancient light, we see not only a moment in time, but also the seeds of our own existence. The iron in your blood was forged in stars that lived and died before the collision began, ensuring that each element present today has its origins in these cosmic events. At the precise moment when Andromeda and our Milky Way started their slow-motion dance of destruction, an unimaginable amount of energy was released across a vast expanse of space. The shock waves from this collision would have sent ripples through the cosmic fabric itself, though these gravitational disturbances are imperceptible to us here on Earth. These ripples, known as gravitational waves, stretch and squeeze space-time in their wake, but they do so with such precision that detecting them requires instruments capable of measuring changes smaller than a proton's diameter. This delicate measurement is akin to feeling the vibrations from a distant earthquake through solid rock. Yet, it is this subtle disturbance that provides us with insights into the forces at play during galactic collisions. While the initial collision occurred billions of years ago, the effects of this event are still being felt within both galaxies today. The stars in each galaxy will take billions more years to fully merge, their orbits gradually altering due to mutual gravitational tugs. This ongoing process is a testament to the enduring influence of cosmic events and how they ripple through time and space. As we observe the light from this ancient event, we are witnessing not just a moment, but also the beginning of a long evolutionary journey for both galaxies. The stars in Andromeda and the Milky Way will gradually become more intermingled as their paths converge over time. This slow merger is a cosmic ballet that will eventually result in a single, larger galaxy. Each star's path, though determined by forces we cannot see, contributes to this grand transformation. In remote regions on Earth, such as underwater caves and deep ocean trenches, researchers have established quiet zones where sound is so minimal that it approaches the silence of space. These locations serve as sanctuaries for listening to faint seismic waves or the subtle hums of Earth's interior. Yet, despite this near silence, these spots are not devoid of sound. They are simply free from human and environmental noise pollution. This quietude is meticulously maintained by removing all external vibrations that could interfere with sensitive recordings. The connection between these terrestrial silent zones and the cosmic void becomes more apparent when considering how both environments reveal faint signals through isolation. Imagine a hydrophone submerged in the Mariana Trench, Earth's deepest point, where pressures exceed 108 megapascals. Here, sound travels through water, which is far denser than the vacuum of space. Yet, the concept of silence remains relevant even within this medium. Just as space telescopes detect faint light emissions from distant galaxies, these hydrophones capture minute pressure variations in water. These signals can be so delicate that they are often compared to the softest rustling of leaves, a whisper barely above the threshold of human hearing. This parallel underscores how both environments function as mediums for detecting extremely faint phenomena. Deep listening zones on Earth and the silent void of space share another similarity: their capacity to amplify the significance of small events. In space, a distant supernova's light may be so dim it is only detectable by specialized instruments, yet its implications are profound. The death of an immense star that could have forged elements crucial for life as we know it. Similarly, in Earth's quiet zones, minute seismic waves can reveal the structure beneath our feet or hint at events from long ago, such as ancient earthquakes. Both environments transform small signals into information-rich datasets, offering insights into processes far beyond immediate perception. When a galactic collision occurs, the resulting shockwaves ripple through space like ripples on a pond. These disturbances are not sound waves, but gravitational waves, ripples in spacetime itself. The detection of these waves by observatories, such as LIGO and Virgo, is akin to listening for faint vibrations that could otherwise be drowned out by louder cosmic noises. This process mirrors the precision required in Earth's quiet zones, where researchers must filter out ambient noise to focus on specific signals. Both approaches require sophisticated technology and a profound understanding of how to extract meaningful information from subtle disturbances. The analogy between space's silence and terrestrial quiet zones extends further when we consider the scale of these environments. The vast distances between stars are so immense that light takes thousands or even millions of years to travel across them. Yet the principles governing sound propagation remain consistent with those on Earth. In both cases, sound travels through a medium. In deep space, it's an absence of particles, and on Earth, it's a fluid or gas. This consistency underscores a fundamental truth. Regardless of scale or environment, certain physical laws govern how information is carried and perceived. In these quiet zones, whether terrestrial or cosmic, time operates differently. While the immediate surroundings may appear serene and unchanging, they are in fact teeming with activity, subtle shifts and signals that accumulate over vast stretches of time. In space, a single photon traveling from a distant quasar may have left its source billions of years ago, only now reaching our telescopes. Similarly, in Earth's quiet zones, the faintest seismic signal can be traced back to an event long past. This temporal disconnect between the immediate and the historical is both humbling and awe-inspiring, reminding us that what we perceive as silence often hides a rich tapestry of events unfolding across incomprehensible spans of time. In the vacuum between stars, sound waves cannot propagate because there is no medium for them to travel through. This absence of air or any other material creates an environment where vibrations, which are essential for sound transmission, simply have nothing to act upon. The molecules that would normally collide and transfer energy in a dense atmosphere are few and far between here. In fact, the density of particles in interstellar space is so low that you could travel many light years before encountering even one atom. Consider this. If sound were possible in the vacuum of deep space, it would be an entirely different phenomenon from what we experience on Earth. Sound waves rely on a medium to carry their energy, but in the near-total void between celestial bodies, there is almost nothing for them to interact with. This lack of interaction means that even the most powerful explosions or collisions would remain silent, as no particles are present to vibrate and transmit the disturbance. Yet, paradoxically, our universe is filled with violent events, supernovae, black hole mergers, that generate immense energy but produce no sound waves in their immediate vicinity. To understand why this silence exists, it's important to consider the scale of space itself. The distance between stars can be measured in light years, meaning that even if a sound wave could somehow propagate through the vacuum, by the time it reached another star or planet, it would have traveled such an immense distance that any original energy would long since have dissipated into the vastness. This is not just a matter of physics. It's also a reminder of how insignificant our human scale is compared to the cosmic expanse. In this context, sound becomes irrelevant because the spaces between celestial bodies are simply too large for it to carry information effectively. Imagine standing in the void between two stars, each 1 millions of kilometers away. The vacuum would be so empty that even if you shouted at the top of your lungs, no air molecules or particles would vibrate to propagate the sound waves. Your voice would fade into nothingness almost instantly, unable to travel more than a few centimeters before losing all energy. This is not just a physical constraint, but also an extraordinary demonstration of how our universe operates on scales so vast that many familiar phenomena cease to function as we know them. Let's delve deeper into the mechanics of sound in space. In interstellar regions, where the density of particles can be less than 1 per cubic meter, sound waves cannot form or propagate effectively. This is because for a wave to travel, there must be a medium capable of transmitting vibrations from particle to particle. Without this medium, the energy from an event, such as a star's explosion, disperses rapidly into the surrounding vacuum rather than forming coherent sound waves. This process underscores how profoundly our experience of sound on Earth differs from what would occur in the emptiness of space. The silence of space also plays a crucial role in the cosmic timeline. Consider that when two galaxies begin to collide, light from this event can take billions of years to reach us. Yet, if sound could exist and travel through interstellar space, it would not only be inaudible, but would also be vastly delayed by the time any waves reached Earth. This delay is a consequence of both the immense distances involved and the lack of particles to carry the sound. In essence, while we might witness the visual spectacle of distant cosmic events with telescopes, the sounds that accompany such phenomena would forever remain out of reach, locked in a silence dictated by the vastness of space itself. Amidst the microgravity environment of interstellar space, human bodies would experience an unusual form of sensory deprivation. Each muscle, accustomed to Earth's gravitational pull, now floats in a state of perpetual suspension, muscles relaxed as if caught in slow motion. The sensation is akin to floating in water, but without resistance. Bones and organs are no longer compressed by gravity's constant weight. Astronauts have reported that even the simplest movements, like turning one's head, can feel disorienting due to the absence of familiar cues. This sensory isolation can be startlingly profound, yet it offers a unique perspective on human physiology. The inner ear, designed for navigation in Earth's gravity, becomes less relevant as spatial orientation shifts from relying on balance to visual cues alone. In this environment, the human body adapts by becoming more attuned to its internal rhythms and external stimuli that are not typically prioritized on Earth. This adaptation can lead to a heightened awareness of one's own heartbeat or breathing patterns, which become palpable in the absence of ambient noise or tactile sensations. Microgravity also affects the perception of time and distance. Astronauts often report experiencing moments where the usual flow of seconds, stretches into an unfamiliar rhythm. The body becomes acutely aware of its position relative to distant objects without gravity's familiar pull to ground it. This disorientation can be a precursor to more profound shifts in perception, akin to how deep-sea divers experience altered sensory thresholds due to changes in pressure and light. In space, the absence of these earthly references creates a new baseline for human awareness. The isolation in microgravity extends beyond physical sensations into psychological realms. Without the constant pull of gravity, everyday tasks such as eating or sleeping take on an unusual dynamic. Floating meals are often consumed with utensils that must be anchored to prevent them from drifting away. A simple action now laden with unexpected complications. This level of attention required for routine activities can lead to a heightened sense of mindfulness, where each movement becomes deliberate and conscious. The brain adapts by reorganizing neural pathways to compensate for the loss of gravity-related sensory inputs. In the midst of a galactic collision, the microgravity environment would be further accentuated by the distant gravitational pulls exerted on matter within the colliding galaxies. These cosmic forces stretch and compress star clusters, creating vast streams of stars in motion. An observer floating within this tumultuous region might notice subtle accelerations as they drift past massive accumulations of dark matter or dense nebulae. The human body, though unaffected by these immense scales directly, would still be acutely aware of its own smallness, a speck adrift amidst the grand architecture of colliding galaxies. Despite the overwhelming scale and disorientation, microgravity can offer a unique form of tranquility. Without gravity's constant tug, the body experiences a profound reduction in strain on joints and muscles. This relief can lead to an almost meditative state where physical discomforts are minimized, allowing for greater mental clarity. In this environment, the mind becomes free to explore concepts beyond immediate sensory inputs, focusing instead on the vastness of space and time that surrounds it. The human body, though isolated from familiar stimuli, finds a new equilibrium within itself, attuned to the infinite yet unburdened by earthly constraints. In 1 billion years, our galaxy, the Milky Way, will be locked in an inexorable dance with its nearest neighbor, Andromeda. This collision is not one of silence, but of gravitational whispers, subtle nudges that guide two massive structures toward each other over cosmic distances. The stars themselves, though tightly packed within their galactic disks, are so sparse on a human scale that the likelihood of direct stellar collisions remains vanishingly small. Yet, the interstellar medium between them will be compressed and heated as the galaxies merge, igniting new star formation in regions where such processes have not occurred for billions of years. The eventual union will take place at an average speed of about 100 kilometers per second, slow by human standards, but rapid on galactic scales. At this rate, the collision will not be a sudden event, but a protracted affair, lasting perhaps 4 billion years from first contact to final coalescence into what astronomers call Milkomeda. In comparison to the billions of years each galaxy has existed in relative isolation, this merging process is an instant. It's as if two ancient entities, having spent their lives apart, are now coming together with a kind of cosmic urgency that defies human comprehension. The stars will not collide like billiard balls. Instead, they will pass by one another, their paths slightly altered by the immense gravitational forces at play. This gentle interaction is what makes galaxy collisions so fascinating. Despite the colossal scale involved, the individual components move with grace and precision. As Milkomeda takes shape, its central supermassive black holes, each currently residing at the heart of the Milky Way and Andromeda, will also begin their intricate waltz. These cosmic behemoths contain masses equivalent to billions of suns, but occupy spaces no larger than a few light days across. As they draw closer, their immense gravitational fields will warp spacetime itself, creating ripples known as gravitational waves that propagate through the universe at the speed of light. These waves are invisible to the eye and inaudible to the ear, yet they carry information about the most extreme events in the cosmos. In 1 billion years, these waves will have traveled far beyond our reach, carrying with them the story of two galaxies' union. The new galactic structure that emerges from this merger will be vastly different from its predecessors. The merged galaxies' spiral arms, once distinct and ordered, will become more chaotic as they intertwine and merge into a grander, more complex shape. This process of reorganization is not unlike the way cities grow organically over time. New suburbs sprouting between established neighborhoods, roads weaving through them in intricate patterns. In Milkomeda, entire star clusters may form that are denser than any seen today, with stars packed so tightly that their light merges into a continuous glow visible from afar. Yet, even as the galaxy evolves, vast regions will remain relatively untouched, maintaining an eerie stillness amid the tumultuous change. One of the most remarkable aspects of this future merger is how silent it all remains. Despite the intense gravitational interactions and star formation events, there is no sound in space to convey these dramatic transformations. The lack of a medium for sound waves to travel through means that even if one were somehow able to hear the collision, it would remain mute to human ears. This absence of sound serves as a poignant reminder of the vast scales involved, scales at which our senses are utterly inadequate. In this billion-year process, time itself stretches and contracts in ways that defy immediate grasp, yet it moves forward with an unyielding consistency. In the far future, when Milkomeda has settled into its new form, it will be a beacon for any distant observers who might gaze upon it millions of years hence. The combined light from billions of stars will shine brightly across intergalactic space, offering evidence of the cosmic dance that once took place between two separate galaxies. This glow will persist long after the initial collision has ended, serving as a lasting testament to the forces that shape our universe. As we consider this distant future, it becomes clear that while individual lives are fleeting, the grand narrative of cosmic evolution unfolds over timescales far beyond human experience. At approximately 50 miles above Earth's surface, the thinning atmosphere marks the beginning of near-vacuum conditions. Here, at the threshold between our planet and space, sound waves begin to falter. Air molecules grow sparse, their density too low for efficient transmission. This boundary is known as the Armstrong Line, where pressure drops below the point human lungs can function without a pressurized suit. Yet, this transition zone is far from silent in its own way. It's a region of dynamic turbulence, where air currents and atmospheric phenomena create complex interactions that can be detected by specialized instruments on satellites. While sound cannot propagate through the vacuum beyond, within this layer, faint whispers of our planet's atmosphere persist, like the final echoes before complete stillness. Above 100 kilometers, in what we call the thermosphere, temperature anomalies begin to dominate. Here, temperatures can soar as high as 2,000 degrees Celsius due to solar radiation striking air molecules at this altitude. Despite these extreme conditions, sound remains elusive. The energy required for waves to propagate through such thin, heated air is enormous, far beyond what our human ears or standard equipment can perceive. This zone, where Earth's atmosphere fades into the void of space, serves as a boundary between two vastly different environments, one governed by gases and pressure, the other by vacuum and electromagnetic radiation. The thermosphere, though part of Earth's envelope, feels more like an outpost on the edge of interstellar space. It is here that astronauts experience their first taste of true silence upon exiting their spacecraft. Interestingly, while this region marks a zone where sound cannot propagate effectively, it is also home to one of the most intense auroras, natural light displays caused by charged particles from the sun interacting with Earth's magnetic field. These luminous curtains of green and red are silent spectacles, visible but inaudible. They remind us that our sensory perceptions are limited. We can see these lights, but cannot hear them. The Armstrong line not only signifies the end of sound propagation, but also marks a shift in how we perceive time within space travel. For astronauts venturing beyond this boundary, every second spent outside Earth's atmosphere is one step closer to an environment where communication relies on radio waves rather than voice. This transition zone encapsulates both our connection to and separation from the familiar world below, a fragile membrane between Earth's warmth and the cold, silent cosmos. The Armstrong line is not merely a static threshold, but a dynamic interface influenced by solar activity and Earth's magnetic field. Solar winds, streams of charged particles emanating from the sun at supersonic speeds, buffet this boundary with relentless force. These winds can compress or expand the outer layers of our atmosphere, shifting the very edge where sound ceases to propagate. During periods of heightened solar activity, such as solar flares, the thermosphere can swell, pushing the Armstrong line higher, sometimes as far as 60 miles above Earth's surface. Conversely, during quieter solar periods, it may descend slightly closer to our planet. This variability underscores how interconnected space and Earth are at this critical juncture. Despite the vastness of space beyond, the immediate environment around this boundary is profoundly influenced by events on the sun, highlighting a cosmic intimacy between distant stars and our home planet. For astronauts venturing past this line, this shift in atmospheric pressure can be disorienting. The sensation of leaving behind a medium that once carried their voice and physical sensations into a realm where neither exist is profound. Yet within this same boundary, there exists another layer of complexity. Ionized particles from the solar wind interact with Earth's magnetic field, creating an auroral glow known as the polar lights. These phenomena occur at altitudes just beyond the Armstrong line, where the air is too thin for sound, but dense enough to produce light shows visible from the ground. This juxtaposition, light without accompanying sound, highlights a peculiarity of our atmosphere's edge. It can be both transparent and opaque in different sensory realms. As we peer into this zone from Earth, we see evidence of cosmic forces at play, yet remain blissfully unaware of their silent symphony. In the dead of night, far from urban noise pollution, if you tune an old-fashioned radio to between 100 and 250 megahertz, you might hear faint hisses of static. This is not interference or signal dropout, but a relic from the birth of our universe, the cosmic microwave background radiation. In space, this radiation permeates every cubic centimeter without obstruction due to the vacuum's silence. The absence of sound allows these ancient photons to travel unimpeded for billions of years, arriving at Earth as a uniform bath of low-energy microwaves. The cosmic microwave background is older than any star or galaxy we can observe. It dates back to when the universe was just 380,000 years old, a mere blink compared to its current age of nearly 14 billion years. The silence of space preserves this radiation, which has cooled from a searing 3,000 degrees Celsius at that time to a frigid minus 270 degrees Celsius today. This temperature is so cold that it approaches absolute zero, where atoms cease their kinetic motion. Such extreme coldness underscores the profound quiet and stability of deep space. While cosmic microwave background radiation whispers in every direction, it also reveals subtle anisotropies, tiny fluctuations in its intensity and polarization. These minuscule differences, amounting to just 1 part in 100,000, provide clues about how matter began clumping together under gravity's pull. Imagine tracing back the history of galaxies through these infinitesimal variations. Each pixel on a map of the universe's infant face tells us something about its eventual structure. In space's silence, the radiation propagates with perfect fidelity, carrying this vital information undisturbed across cosmic time. On Earth, detecting such faint signals requires precise instruments and locations far removed from human-made noise. Yet in space itself, there is no need for silencing devices or remote observatories. The inherent quiet facilitates unobstructed detection of these ancient photons. A single photon traveling through deep space can do so for billions of years without encountering anything to impede its path. This contrasts sharply with sound waves on Earth, which dissipate after mere kilometers due to interaction with molecules in the atmosphere. Despite the silence that allows cosmic microwave background radiation to persist unaltered, humans have developed technologies capable of hearing this echo from the universe's infancy. Satellites orbiting high above our planet's noisy surface collect data that scientists then analyze using complex algorithms and supercomputers. These tools help decode the patterns within the radiation, revealing insights into the early conditions of the cosmos. The quiet of space not only preserves, but also magnifies its significance, offering us a direct window into the origins of everything. Every second spent listening to cosmic microwave background radiation connects us to an era when our universe was just beginning to expand from its initial dense state. Each detected photon carries within it a story written in the fabric of time itself, how quantum fluctuations seeded the structures that would eventually become galaxies, stars, and planets. In this vast silence, we find ourselves part of something far greater than ourselves, where each measurement of temperature or polarization brings us closer to understanding not just how the universe began, but why it continues to evolve as it does today. As instruments like LIGO and Virgo detect gravitational waves from colliding black holes, they capture silent events that ripple through spacetime with an accuracy of less than a billionth of a meter. These ripples are disturbances in the very fabric of reality itself, traveling at the speed of light across billions of light years. What we perceive as sound on Earth, vibrations carried by air molecules, is utterly meaningless here. The detectors pick up minute distortions, converting them into data that can tell us about events far beyond our reach. Imagine two black holes, each with a mass hundreds or thousands of times greater than our Sun, orbiting closer and closer until they merge. This collision is not visible but detectable through these minute vibrations in spacetime. The energy released during such an event exceeds the luminosity of all stars combined over a period of mere seconds. Yet this incredible phenomenon occurs in regions where sound could never carry information. Instead, we listen to the universe's silence with precision-engineered instruments on Earth. These detectors operate using interferometry, splitting laser beams and sending them down miles-long vacuum tunnels at right angles before recombining. When gravitational waves pass through, they cause minute differences in path length for the lasers, detectable as subtle shifts in interference patterns. The sensitivity required is such that these devices can measure changes equivalent to the width of a proton over distances stretching kilometers. This technology allows us to witness cosmic collisions without ever hearing them. Consider the paradox of what we are detecting: signals that propagate across unfathomable distances, but would be imperceptible were you standing nearby during the event. The sheer scale of these phenomena defies comprehension. Imagine being close enough to observe two supermassive black holes spiraling into each other. Yet, all around you, there would be no sound because there is nothing to carry it. Instead, our instruments translate this silence into a symphony of data that reveals the universe's most cataclysmic processes. In addition to measuring gravitational waves, these detectors have also mapped out the distribution of dark matter in nearby galaxies by analyzing how light and gravitational waves are affected as they traverse regions of varying mass density. This technique provides us with insights not only into black hole collisions, but also into the invisible structure that binds our galaxy together. Each measurement adds another piece to the cosmic puzzle, illustrating both the vastness and the intricacy of the universe. Each detection represents a snapshot in time from events that occurred light years away, often billions of years ago. The information we gather today is not just about what happened, it also offers glimpses into how our understanding evolves with new discoveries. These silent ripples are messengers from epochs when the first stars were igniting and galaxies were still forming. As we continue to refine our techniques and expand our network of detectors, we inch closer to comprehending the true nature of space-time and its role in shaping the universe around us. In these instruments, precision is paramount. Each mirror suspended by wires thinner than human hair must remain perfectly still to avoid obscuring the subtlest vibrations from distant cataclysms. The mirrors are so exquisitely balanced that they can detect movements smaller than a proton's width. This level of stability is maintained through an elaborate system involving vacuum chambers and active seismic isolation systems designed to shield against even the faintest tremors on Earth's surface. To ensure accuracy, scientists must account for every potential source of interference, from thermal fluctuations in the equipment itself to tidal forces exerted by our own moon. Each detection is a triumph over noise, both literal and figurative. The signal-to-noise ratio in these experiments approaches unimaginable extremes. It takes extraordinary effort to distinguish the true cosmic tremors from terrestrial vibrations or instrument artifacts. This meticulous filtering process underscores the rarity of such events. While black hole collisions occur frequently on cosmological timescales, they are exceedingly rare when considering the vast distances involved. Each confirmed detection represents a minuscule fraction of the universe's total activity, a single note amidst an orchestra playing at incomprehensible scales. Despite this improbability, our ability to detect these gravitational waves has expanded our knowledge of black hole populations and their distribution across space. This data challenges previous assumptions about how often such collisions occur and what conditions might facilitate them. As we refine our methods, the universe reveals itself in new dimensions, offering insights into both its violent past and its serene present, where space-time ripples carry secrets from epochs long gone, but still echoing through the cosmic fabric today. In 1 billion years, our galaxy will merge with Andromeda, their stars swirling in an intricate ballet of gravitational forces. This collision, though cataclysmic on cosmic scales, will be nearly silent. No sound can travel through the vacuum between these galaxies. The immense distances ensure that any potential medium for sound propagation is far too sparse to carry waves. As star clusters approach each other at hundreds of kilometers per second, they exchange energy in a slow-motion collision. To an observer within this future merged galaxy, the absence of sound would be a stark reminder of the vacuum's pervasive silence. Yet, paradoxically, the merger's immense energy output will generate light visible across vast cosmic distances. The stars themselves are finite entities, born from collapsing gas clouds and destined to die in fiery explosions or quiet collapses. Once all these stars have exhausted their nuclear fuel, they will either fade into black dwarfs or collapse into neutron stars or black holes. The universe, bereft of stellar radiation sources, will grow colder still, with temperatures approaching absolute zero. In this deep future, the void between galaxies will become even more isolated, so empty that not even quantum fluctuations would be detectable over cosmic scales. This profound emptiness contrasts sharply with the vibrant life and light we see today in our night skies. Despite its desolate appearance, this final state of the cosmos is a testament to the relentless laws of physics. Consider now how sound travels. It requires particles colliding and transferring energy through vibrations. In intergalactic space, where matter density approaches zero, such interactions are non-existent. Even black holes, which can emit gravitational waves when they collide, do not create acoustic disturbances. The silence is absolute because there is no medium to carry the waves. Yet within this void, cosmic phenomena continue. Gravitational waves ripple through spacetime like invisible ripples in a pond. These subtle distortions travel across the universe, carrying information about distant events without making a sound. This silent communication underscores the peculiar nature of space itself, where vast distances and near absence of matter create conditions that defy our sensory expectations. The vacuum silence is not merely the absence of sound. It is also a consequence of how energy propagates in the universe. Photons can travel through this void at light speed, carrying information about distant stars and galaxies across billions of years. In contrast, sound waves require a medium to propagate and are confined by their need for matter interactions. This paradox highlights the peculiar nature of electromagnetic radiation compared to mechanical waves like sound. As we peer into the future, where all stars have burned out and the universe cools, even this faint light will eventually fade. The cosmos will become an immense, dark expanse, a place where not even photons can travel far without interacting with something, be it dust or residual gas. The concept of time itself changes in such an empty universe. Billions upon billions of years pass by, and yet the vast majority of this future will be devoid of significant events. Stars that once shone brightly have long since faded into darkness, their light reaching us eons ago. In this final era, if any form of life were to exist, it would find itself in an almost eternal night. The absence of sound waves and the rarity of electromagnetic signals mean that communication between distant points in the universe becomes impossible. This isolation is profound not just because of the lack of sounds or light, but also because of the sheer emptiness. Space is so vast that no event can cross them within measurable time frames. Returning to our initial observation about space's silence, we find a new perspective on its nature. The vacuum of deep space, once described as merely lacking an atmosphere, now appears as a place where physics itself enforces silence across cosmic distances. In this future state, when all stars have died and the universe has cooled, sound would be even more impossible than it is today. There simply wouldn't be enough matter to carry waves or even for quantum fluctuations to occur meaningfully. This profound emptiness is not just a lack of noise, but an extreme condition where the very fabric of space itself seems to whisper nothingness across billions of light years. As we contemplate this final state, we realize that silence in space is both inevitable and eternal, a quiet testament to the universe's relentless journey toward entropy. The vast emptiness of space remains a silent canvas, where even the sparsest particles are too distant to carry sound. As our journey through this cosmic void draws quietly to its end, I hope you've found peace in these starlit moments. Thank you for joining us on this peaceful voyage tonight. If you enjoyed it, please subscribe and leave a like. Sweet dreams, and until next time, farewell from the depths of space.